If you pick a random star in the Milky Way, odds are it's a red dwarf. They make up roughly 70% of our galaxy, and for decades, they have provided the best mathematical odds for finding habitable worlds. But the math hides a physical problem. Young red dwarfs are violently radioactive, often blasting their surrounding planets with stellar flares and extreme ultraviolet radiation. This has led to a long-standing debate over whether these planets can keep their air or if the radiation strips them down to bare rock within the first billion years. Because we couldn't see through the blinding glare of the host stars, this argument remained locked in the realm of theory. We lacked the technology to observe the planetary surfaces beneath the light. The James Webb Space Telescope was built to solve this by capturing light at mid-infrared wavelengths. It has the physical gathering power required to ignore the starlight and detect the incredibly faint thermal emissions radiating from the planet's own crust. Identifying the surface of a single world provides the missing variable needed to test habitability models for billions of other planets across the galaxy. The first target for this technique is a super-Earth called LHS 3844b. Located 48 light-years away, this rocky world is locked by gravity into a brutal 11-hour orbit around its star. This world is tidally locked. One side never sees light, while the dayside bakes at 1300 degrees Fahrenheit, a temperature that would instantly melt aluminum. In the infrared spectrum, the host star is 2,000 times brighter than the planet. At this distance, isolating the planet's heat is equivalent to measuring the glow of a single candle held next to a stadium spotlight. To bypass the glare, astronomers wait for the planet to swing behind the star. During the secondary eclipse, the telescope captures the star's light alone, locking in the exact value of its baseline starlight. As the planet re-emerges, the telescope measures the combined light of both bodies. The team then mathematically subtracts the star's baseline from the total, isolating the tiny remaining thermal signature of the planet itself. This process allows researchers to extract a pure, uncorrupted thermal fingerprint, providing a direct measurement of the exoplanet's physical properties. The Webb data immediately ruled out any thick atmosphere of carbon dioxide or sulfur with extreme statistical confidence. Without an atmosphere, there is no weather or wind to push heat around the planet. The signal Webb received is coming directly from a bare, exposed crust. Different minerals have unique absorption bands in the mid-infrared, called restolin features. These act as a definitive chemical fingerprint for solid rock. The research team compared the planet's fingerprint against a library of laboratory samples. They found that granite, the rock that builds continents on Earth, was a near impossible match for this data. The data perfectly matched a sample of dark volcanic basalt collected from the 1919 Kilauea eruption in Hawaii. This 100-year-old rock, ground into powder in a lab, provided a near-exact fit for a world 48 light-years away. The planet's reflectivity, or albedo, is around 0.14. It's the shade of coal dust or black asphalt, as dark as our own moon. By matching these specific thermal signatures, we have successfully performed the first true geology on an interstellar world without ever leaving Earth orbit. The reality of LHS 3844b forces us to reconsider those billions of other red dwarf systems. If this world is representative, our expectations for finding life around these stars must be reset. The data supports a harsh mechanical theory. A rocky world orbiting close to a red dwarf, without a massive magnetic shield, will have its entire atmosphere stripped away by stellar radiation. Thousands of exoplanets previously labeled as potentially habitable in news reports may actually be entirely dead, weathered slabs of cooled mantle. This shift marks a transition in astronomy, where theoretical simulations are finally being replaced by hard, undeniable data. The Webb telescope is already applying this subtraction technique to other rocky targets, building the first accurate statistical census of planetary survival. The first rocky planet we have truly read is a baked, airless stone. That silence provides a physical anchor for our models, replacing years of speculation with a hard, unyielding data point.